So folks, Alex here. So today I really wanted to talk about this peculiar phenomena that is called false sharing. So false sharing is a phenomenon related to how the modern CPUs work with the memory, right? Particularly with the caching subsystem. So long story short is this, right? So when your program running on a particular core at some point wants to like read or write data on a particular address, like deadbeef, um, it would not negotiate that request with the RAM chip itself, right? So instead, that request will be served by a caching subsystem and probably by the L1 cache that is like the closest one to the core, right? And of course, this is done, for performance reasons as usual. And performance difference here is, due to like L1 cache being like physically very close to the core. It's being like implemented as a part of the CPU itself. But also the difference is that the cache memory, the implementation of that memory cells is very different from what we have here. So this is something called DRAM, and it's based on capacitance. It's just a huge array of little capacitors that need to be like charged and discharged in order for memory to work. But these guys are based on SRAM. SRAM is based on latching circuits, which are very fast. There is no capacitance, no nothing. But the latching circuits are kind of more complex and take up more space on the chip. So these are more expensive, and that's why you cannot like create SRAM like SRAM as big basically as DRAM here. So that's why. What's important for us as software developers is that each core here, no matter how many cores you have, typically has its own set of L1 and L2 caches, right? And L3 cache is typically shared between all the cores. So this can actually be pretty profound. That everyone has its own view on the memory, because that view, eventually, ultimately, it needs to be synchronized between all the cores and the RAM itself. The other very kind of important piece to that is that even if you're reading just a single byte of data, the RAM will give you a something known as cache line worth of data, right? So 64 bytes at a time. So you read this deadbeef pointer, but you get this deadbeef plus, every offset all the way up to 64. This whole chunk, right? Which is pretty important because it kind of, it implements this kind of temporal and spatial proximity optimization, basically, right? Also, another point here is that you not only need to read memory, sometimes you need to write it. Oh, fire truck. Hi, trucky. You need to write memory as well, right? And let's say here, let's say, you have like two cores, right? And these two cores have a particular address that beef being kind of mapped as a cache line in their correspondent L1 caches. But now imagine that core 0 is actually trying to modify the value foo, which is just a U64 value within that cache line. That would mean that actually that cache line, the whole thing, needs to be invalidated and synchronized back to the RAM chip. But not only that, all the caches, all the kind of copies of that cache line that can be held by the rest of the CPU by different cores, right? All those need to be invalidated and renegotiated with the central memory as well, which actually can lead to a massive spike in kind of cache misses, right? Which is not what you want to see at all, and can actually lead to a very poor performance, right? So again, core 0 modifies foo, core 1 tries to read bar, right? Not foo. It doesn't want to foo at all. But core 1 still pays this like huge penalty because they basically share the same cache line. So that's what's called false sharing, and that's not good at all. And today I want to see, I want to do like a couple of experiments. So I want to see if I can verify that the cache line length is actually 64 bytes, right? And it should be pretty easy to do, right? Because like poking into the memory within the cache line is, relatively cheap. And when like in particular, when on a particular offset, I will start seeing a like sharp spike of kind of latency. Basically I will know that this I have reached the kind of the end of the cache line, basically. You know what I mean, right? And this, well, for that we will basically create a couple of threads, and the one thread will be hammering that value foo, and the other one will be reading value bar. And what we're gonna see is that, hopefully gonna see, is that that whole program will report a massive amount of CPU cache misses, right? So that's what we're gonna see. So let's focus on getting the cache line size first. So something like this: unsafe entry, unsafe function entry, right? So first I wanna allocate some memory. So let ptr is like std alloc allocate 0, std alloc layout from size align, and maybe let's allocate like a page worth of memory, right? So here I'd suppose to I don't know, if it's like is null, then I'll just panic, can't allocate or something, right? So in order to play with the caches and measure times in such a kind of fine grain, I will be needing two things. So use std arch x this, and then for the cache flushing, I think there is something like clflush, right? Clflush invalidates and flushes the cache line that contains p from all the levels. So just provide a pointer and it will evict that line from all the caches. And also for the time measurement, it's like rtd scp, something like that, right? And this is reads the current value of the processor timestamp counter and monotonically increments the timestamp counter MSR every clock, blah, blah, blah. So this is basically like a very high performance, fine-grained timer that is provided by the CPU itself. And save function time, and I want to say that this is like U64 or something, and let or I guess auxiliary value is U32 0, and we will return DTSP mute aux, something like that. Mutable value aux, mutable of course, and like that. Yeah, so this will be our kind of T0 equals to time kind of thing, right? And yeah, so we've read this, right? So I wanna like flush that pointer out of caches completely right away, right? And something like for offset in from 0 to 128 or something, for attempt in from 0 to let's say 124 attempts. For attempts, let's maybe create like results or something. Let mute results. So like a vec with capacity attempts, right? And what we're gonna do, we will try to flush the pointer. We will try to flush the pointer at offsets, right? We'll probably need to memory enhance, so basically need to like synchronize all the memory operations all the way up to that point, right? So fence like this, right? And now I want to read the value of that pointer. So I want to cache that pointer first and then reach out to the pointer plus some offset. So std ptr reads volatile pointer, and I don't care what is the value that we just read. Let's maybe like synchronize the memory here, and then let's say like t0 equals to time, right? t1 to time, and in between we will try to read pointer at offsets, right? And we will try to store the results. So like push t1 minus t0, something like that, right? Yeah, we probably don't need that. And then, you know, we've collected, you know, some data, basically a bunch of attempts. And I want to just print line the kind of offset and, I don't know, median of the results, something like results, maybe attempts, like that. And this is like median, right? Like that. Cool. And fence, read volatile. Let's try to run it. So cargo run bin cache line. Cache line 27. Attempts. 124. Yeah, the line is 1. Results push this. Oh, of course. So silly of me. Okay, so let's see. So basically now we have an output data in a format where, you know, we've read this. So what's happening? We've read this pointer, right? Not even that. So I evicted the pointer and pointer plus offset from the cache. I waited for them to be completely evicted. Then I reread the pointer back to the cache, right? And you know, I waited for that to actually complete, right? And then I'm trying to like probe how much time it takes to read that pointer plus some offset, right? And basically I'm just printing this. So for an offset, this, you will get this amount of time. And what we see in here is that the values here, you know, like 45, 90, 45 are kind of all the same all the way up to here, right? So 63 takes 90 like cycles basically to read. But now 64 all of a sudden takes 720 cycles. and you know, it basically becomes huge from now on, right? And I think we can maybe do even this. Yeah, why not? So 90, 90, 90, 63 gives you 90, and 64 gives you this huge number, and it stays huge after all, which basically means that the price that you pay for accessing cached memory with an offset all the way up to 63 is basically negligible. It's like, yeah, it's 90 cycles. And then when the cache line ends, right, on that offset, you know, that becomes like the latency becomes huge again. So that's basically proves that, you know, there is a cache line, and the cache line size is actually 64, and it's 64 because, you know, we are starting from the offset 0. So from 0 to 63, it's 64. Okay, so I think this concludes that yes, the cache line is real, and if you like, if the cache line is being evicted from the L1 cache, that would mean that the latency becomes huge. So don't evict your cache lines, right? And the other experiment that we wanted to try is, let's call it, how are we gonna call it? Maybe like false sharing, right? False sharing. And for that, let's say we have like struct, let's call it probe, right? And for that probe, we have this foo, which is, you know, U64, and bar, which is U64 as well, right? And I want to have this like, I don't know, container or something. And container is basically this. It's like a mute pointer to this probe, right? And for that, I want to derive copy and clone, right? But I also want to like unsafe impl maybe sync for container and send for container, right? And what is the size of that probe? The size is 16, so I really want to kind of force it to be properly aligned. So wrapper C and align 64. So now the size should be 64. Yeah. Cool. So here, let's see. Let's create is this container, and like inner is what? Is a mute pointer to this. So mute pointer to probe, which is like foo is 0 and bar is 0 as well, right? And container doesn't need to be mutable though, I'm not sure, we'll see. Okay, so let T0 is basically std threads spawn, and then move this. So here we wanna do what? We wanna thrash the value foo here. So like container inner, we need to kinda dereference it like foo. Let's just increment that in a loop, something, right? And let's create another thread like T1, and here we will just be like bar and std ptr read volatile. We'll be just reading the bar. So this is exactly what we were talking about, right? So I'm writing into that foo in thread T0, and I'm reading value bar in T1, right? So T0 join unwrap and T1 join unwrap. Okay. And I wanna do this. Allow path statements. Okay. And we don't need that, right? Cool. So this is exactly what we wanted here, right? So I have 2 threads, 2 cores. Technically, like, to be like completely precise, I need to kind of, pin those threads to like 2 different cores, but I'm pretty sure it will be working as this, working fine as this, right? And let's maybe try to cargo build, right? And do something like perf target debug false sharing, right? So I want to see how many cache misses that whole shenanigan produces. So let's run it for some time, and you will see that indeed that like access pattern modifying foo in one thread and reading bar in other thread produces 97% of all cache misses, which is kind of insane. Like, again, I mean, if you know about cache lines and false sharing, this kind of becomes, extremely trivial. Of like, you might be seeing this and thinking like, yeah, of course, so obvious. But if you don't, or if you are not like expecting to see this, this might be actually pretty weird. So let's see if I can fix it by just maybe sticking something in between. So like, I don't know, like buffer, and like, let's say buffer len or something like that. Use size and buffer len 0, and I want that to be like u8 with len buffer len, something like that, right? And that would be buffer like zeros buffer len, right? So this doesn't change anything, right? So with buffer len 0, the size of the probe is still 64. It's still just a single cache line, right? So these 2 guys, foo and bar, live within the same cache line still, right? So if I do this, I kind of just build and I rerun that experiment, it's the same thing. 97% of all cache refs are being misread, basically, cache misses, right? But what if I said, well, what if buffer len becomes 32 maybe? Or 32 isn't enough. Let's say 64. So now the probe size is 128. See? Which means that the memory that is occupied by that probe actually takes up 2 cache lines. And bar, being on the kind of, lower end of that memory, now would not occupy the same cache line as foo. And now writing to foo should not evict the cache for bar. And technically now we should not see that like catastrophic situation where we are like missing a lot of caches. So let's cargo build again. Let's measure the perf. And you would see that, yes, cache misses are still there. There is still some. And I would say it's still kind of a lot, but it's much less. Let's see, what if I did 128? It's kind of a lot still, but 15%, I don't know. 15% is kind of a lot, but it proves the point, at least, that yes, actually, false sharing is a real thing, and yes, you can end up in a very bad kind of situation performance-wise here, right? So yeah, I, I think this is kind of interesting. This is something that is usually hidden from the programmer, that is usually hidden from your eyes, right? This is considered to be an implementation detail, but it has a very, very real consequence to your program's runtime, right? So hopefully that was interesting. Hopefully that was useful for some of you, and yeah, I guess if you have any like comments, don't hesitate to leave them. That would help the channel to grow. But yeah, that's it. That's all I have, and I'll talk to you the next time. See you, folks.